Hey everybody, it's Friday, May 7th. As you can see here in the aim for today, our goal for today's video is going to be to review the two free response questions assigned yesterday under the title AP Physics FRQ Review Day 14. Now, I would just like to apologize in advance for this screencastify thing showing down here at the bottom of the screen. I just spent 45 minutes recording this video only to realize that the program had crashed 14 seconds into it and really don't want to experience that again, sitting in my room for 45 minutes talking to no one. And so I will take that off the screen as is necessary if it gets in the way. But for now, I'm going to keep that there. I apologize for the nuisance. This question here, 12 points, 25 minutes, says a block is initially at position x equals 0 and in contact with an uncompressed spring of negligible mass. The block is pushed back along a frictionless surface from position x equals 0 to x equals negative d, as shown above, compressing the spring by an amount delta x equals d. The block is then released. At x equals 0, the block enters a rough part of the track and eventually comes to rest at position x equals 3d. It says here the coefficient of kinetic friction between the block and the rough track is mu. Of course, you can see here the track is colored differently for the section of it that is rough. It says here on the axes below, sketch and label graphs of the following two quantities as a function of the position of the block between x equals negative d and x equals 3d. You do not need to calculate values for the vertical axis, but the same vertical scale should be used for both quantities. So we got the kinetic energy and the potential energy. Now this is in the way. So there are a couple of things that we want to say here for this problem in terms of drawing the graph. I think what you should definitely realize is that when it comes to a big graphing question like this, it's a really smart idea to just take a minute at the top and plan. If you've ever heard in shop the phrase like measure twice, cut once, it's so that you can avoid having to deal with all the annoyance, associated with making mistakes on the back end. So if you plan accordingly in the beginning, it's going to be a lot easier to do this correctly at the end. So we've got to show on this graph the kinetic energy of the block and the potential energy of the block spring system. Now, there are a couple of things that this graph is going to have to show. This graph is first going to have to show that as we go backward from 0 to negative d, the elastic potential energy increases. Now, we'll talk in a little bit about how the increase should be represented on the graph, or in other words, how the shape of the graph should look. But at any rate, as this block comes back from a position of x equals 0 back to here at negative d, where it's compressing the spring, the elastic potential energy should increase. Then, as the block is launched, as the spring decompresses itself, going from negative d to 0, we should see two things. We should see the elastic potential energy come down. The spring is going to get closer and closer to its equilibrium position, so it's going to lose its elastic potential energy. And we should see that the kinetic energy of the block should increase accordingly, right? Because the increase in kinetic energy of the block is going to be directly caused by the decrease in the elastic potential energy. Then, from here to here, we should see a couple things. The first thing is, as the block continues to slide, it's sliding along a rough track with a coefficient of friction. And because the coefficient of friction is listed as mu, we know the force of friction is not going to be 0. Because the kinetic energy is given by the equation 1/2 mv squared, we should have some sense here that this force of friction is going to slow down the object. And if the speed is decreasing, the kinetic energy is going to decrease, because the kinetic energy is proportional to v squared. So what we should see is that the kinetic energy of the block decreases along this entire distance. What should also be noted, I think, is that the spring stops decompressing itself here. And so that means for this whole part, the spring energy is going to be 0. That's at least the basic point. So now when we come over to the graph, there are a couple things we need to think about. I think the first thing that we should think about is the left part of this graph is going to be really important. And by the left part, I mean to the left of this vertical energy axis. On the left, we should be really concerned with the spring. The spring is going to govern everything, because what's happening to the spring affects, obviously, the spring potential energy, but it also is going to affect the kinetic energy. To the right of this axis, we really want to concern ourselves with the block, because the work that's done by friction is going to decrease the kinetic energy. All right, so let's now come over here. Now, that's the first thing we should say, right? Is that like we just want to consider these other, like the particulars of the situation. I think what we should also note, which I'm going to write here too, so like these are like item number one, stuff we got to consider. Item number two that we have to consider is that conservation of energy definitely has to be true here. And everything that we show should be in accordance with the law of conservation of energy. Speaking of which, let's just go ahead and get that out of the way right now. The first thing we'll say is this is going to be our maximum energy value. So our maximum energy value for the spring potential energy, which is going to be the only kind of energy when the spring is fully compressed, is going to be, what is this? 1, 2, 3, 4, 5, 6 units high. That energy is going to come down. The kinetic energy is going to go up. And by the time it gets to 0, it's going to be all kinetic energy. So the kinetic energy is going to start at 0, and it's going to be all kinetic energy. And the spring energy is going to go from fully maximized at x equals negative d to 0 at x equals 0. What I said before is also going to be relevant here, that once the spring decompresses at x equals 0, there's no spring energy. And so that means this whole time from 0 to 3D, the spring energy here is just going to be 0. Now, you see how I'm coloring this in? When a value is equal to 0, I like to color it in so that they can really tell when they're grading the paper, oh, that's not just the x-axis here. This kid is intentionally trying to say that this value is 0 here at this point in the graph. All right, so that's our first move. Now, let's go to the left side of the graph. This is where we're going to spend the bulk of our time on. Let's talk about the spring. So how the heck are we going to figure out what the elastic potential energy should look like to the left of this energy axis? Well, according to the equation, 1/2 kx squared, the elastic potential energy is directly proportional to x squared. What that tells us is that we are going to see an exponential relationship here between the spring energy and the distance. Now, this is the graph we usually see. And this, it's important to realize, is showing the compression distance increasing this way. But what this graph is showing is the compression distance increasing this way. And so what you need to realize here at first is that to some degree, this graph is going to show the opposite of what the traditional graph usually looks like. We're going to see as this goes from 0 to its maximum compression distance, we're going to see this big increase in the energy. Now, it's going to look a little something like that. And I already told you, I don't want you to draw this more than once. I would like you to come up with a plan and then draw, but I wanted to just make a sketch because there are some other important considerations that we should make. Like what? Well, the first thing that we should say here is that you should know by now when this spring gets to the halfway point, and I'm going to write A for amplitude here, even though this is not a simple harmonic motion question, just because we've looked at that recently. But the point here is when the spring is at half of the maximum compression distance, what we see here is that the spring energy, because the x is squared, is actually going to be a quarter of its maximum value. And so we should see this go down to about a quarter of its maximum value by the time it gets to the halfway point. Now here, this at maximum energy we said was 1, 2, 3, 4, 5, 6 units above. So that means at the halfway point here, it should be at a quarter of 6, which is about 1.25. So that means that should be like a teensy little bit higher. That's fine. Like what we have there is actually probably going to be fine. But I'd like to do this as accurately as I can, especially considering the fact that my drawing ability is hindered with this digital pen. There's one more thing that we could consider, though, as we're drawing this graph. So I'm going to I'll leave this up for a second. What we should also say is that we also mentioned, and I'm going to actually write this down here because I think it's important. We also mentioned that the 50-50 split in elastic potential energy and kinetic energy occurs when the position for the spring compression is 0.707 of the amplitude. And so that means at about 70% of the way 70% of the compression distance left. Notice this would be 75%, so that's going to be like here. We should be at about half the energy. And notice we're a little lower than the 3 line there. So we're going to want to put this about through that dot there. Now, of course, you don't need to go as nuts with these values as I am right now, but I do think it is important for you to remember that these things are true about the spring. We're going to show this come down. It's going to pass through there. It's going to pass through there. We're going to have it reach the bottom there nice and gently. Now, of course, you can always smooth over your mistakes, and I'd definitely be doing this if I was taking this test because I am bad at drawing. To try to make the line look a little smoother when you have it wobbling, just sort of make it a shade darker, and then it looks a little better. I mean, obviously, it's not perfect. It's pretty bad, actually, but it's good enough for full credit. So there's our potential energy line. And now we want to label that U with a subscript S. Now I'm actually going to totally divide this off so we're not confusing anything here. That's our elastic potential energy graph. Now, as I already mentioned here, the kinetic energy part of this should be easy. The decrease in the spring potential energy directly affects the kinetic energy because the decrease in the elastic potential energy is exactly equal to the increase in kinetic energy. So you really only have a couple of considerations as you're drawing this. Your considerations are, it's got to start here, it's got to end there, and it always has to be drawn in such a way that the total energy is conserved. So that means here, it's going to end up looking a little something like this. Now, of course, that's not perfect, but we can color it in a little bit, smooth off the lines, and now we can see here that more or less that's pretty much there. Now, of course, we don't want this to even look like it's dipping back down, and so we'll try to just draw this as one solid arc. But that's the basic idea here. Now, how do we know that that's pretty much there? Well, when this is 1, the kinetic energy's got to be 5. And it's pretty much 5. When the kinetic energy is 3, the potential energy is 3. It's always conserving energy here. When this thing is 1, we come up, that's 5. And so 1 plus 5 is 6. It's showing the same total amount of energy every time. And so, of course, because that's our kinetic energy, we're going to label that with a K. All right, so we basically got the left now taken care of. Now we need to focus on the right. Now, it should be clear to everybody. It should have been clear when you first read this question that the kinetic energy's got to be decreasing on the right-hand side of this graph. As the object slides from 0 to 3D, friction is doing work on this block, which is decreasing its kinetic energy. But of course, the real thing we have to be careful of is how the friction is decreasing the kinetic energy, specifically with how the kinetic energy is varying as a function of the distance. Well, we should know by now that when friction slows down an object, if we want to apply friction and work concepts together, we say here that the work that's done by friction is equal to the change in kinetic energy. Now, of course, if you actually wrote that out, you would get KE final minus KE initial. And then, of course, the final kinetic energy is going to be 0 if the object comes to a stop. And so that really means here that the work that's done by friction is going to be equal to the negative of the initial kinetic energy here. And so we can use some absolute value bars here so as to not go absolutely insane, but we'll say work due to friction equals initial kinetic energy. This whole time I was using I. I'll go back to O. Now, what exactly does that mean? Well, it means the kinetic energy is going to be equal to the force of friction times the displacement. And so what that tells us is the kinetic energy is directly proportional to the displacement. That's an important thing to realize. So here, you want to pay attention to a few things in particular. The first is that the kinetic energy's got to decrease. But when we're making an energy consideration, the point is the kinetic energy is going to decrease linearly with the distance. Now, this part is going to be hard to draw. You're going to have to bear with me. I am not an art student. Oh my gosh, already it's not steep enough. But we'll just kind of show it going here. Obviously on the test, you're going to want to use a ruler. We're going to show this come down. It's hitting 0, almost there. We're just going to try to darken that up to make it look really like it's decreasing linearly. And that's that. that part of it is supposed to be linear. Of course, you're going to want to use a ruler when you're doing this, but that's the basic idea. Take a second to pause this video here right now and sketch this graph. And when you hit play, we'll move on. All right, let's take a look at the scoring guide. Take a look at the scoring guide here. You can see basically the graph that I just drew, of course, much better though. And the only real difference is that they've made the maximum energy on the 5th line instead of the 6th line. It's no big deal though. Here, they give you 1 point for sketching either energy curve with a reasonably correct shape between x equals negative d and x equals 0, with 0 and maximum values at the correct locations. So that just basically means for the kinetic energy, putting the 0 here and the max there, and the for the potential energy, the maximum here and the 0 there. You got 1 point for sketching two curves from x equals negative d to x equals 0 with shapes and values such that the total energy is constant, even if the curves are correct. Even if the curves are incorrect, excuse me. You get 1 point for sketching potential energy equal to 0 from x equals 0 to x equals 3d. And you get 1 point for sketching kinetic energy as a linear function from its maximum value at x equals 0 to x equals 3d. Now, let's be clear. If you totally struggled with this part of the graph, you would have lost this point. If you drew that part of the graph like this, thinking they were linear, and then just said, well, the kinetic energy is linear too, because I'm not really sure what's going on, it's important to realize that response would have earned you 3 points if you just put the potential energy as 0 over there. Make sure you fill out the whole graph. Make sure you read the instructions. Make sure you answered these questions as much as you possibly can. Because if you got this totally wrong, like didn't realize the energy was supposed to decrease exponentially here and it was supposed to be mirrored for the kinetic energy, if you sketch them like this, such that the energy is always added to the same total value, and the energy came down like this, linearly, for the kinetic energy, and that the energy was 0 when the spring wasn't compressed or stretched, you would have gotten 3 out of 4 points. 3 out of 4 points is a 5 on this test. Take a second to pause this video here. Make sure you understand all aspects of the scoring guide. When you hit play, we'll move on. All right, moving on here. The next part of this question, part B, says the spring is now compressed twice as much to delta x equals 2d. A student is asked to predict whether the final position of the block will be twice as far at x equals 6d. The student reasons that since the spring will be compressed twice as much as before, the block will have more energy when it leaves the spring, so it will slide farther along the trap before stopping at position x equals 6d. That's an important thing to realize here. Now, it says which aspects of the student's reasoning, if any, are correct. Explain how you arrived at your answer. Now, the first thing you need to realize here is that there are a few parts of this that are correct. It says the student reasons that the spring will be compressed twice as much before, so the block will have more energy when it leaves the spring. Yeah. They also say so it will slide farther along the track, and that much is definitely true as well. So what I wrote here is the student is correct that if the spring is compressed more, the spring will have more energy. According to the equation, US equals 1/2 kx squared, the elastic potential energy is directly proportional to the square of the distance from the equilibrium position. So if the spring is compressed more, it will store more energy. Now, what I also said here, and you'll see in a second that this doesn't count for anything, is that the student is correct that the block will slide farther. If the spring stores more energy when it's compressed more, then it'll give more kinetic energy to the block, which means the block will slide farther down the track. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. When you hit play, we'll move on. All right, moving on to the scoring guide here, we see this was just a one-pointer. 1 point for identifying that the student is correct that the block will have more energy when it leaves the spring. That's it. Now notice the actual question, which I think you should always follow the instructions for, said explain how you arrived at your answer. They didn't even really give points for that on the scoring guide, which I thought was kind of bizarre. But either way, student is correct that the block will have more energy when it leaves the spring. Take a second to pause this video here, write that down, making sure you understand all aspects of the scoring guide. When you hit play, we'll move on. All right, moving on here. The next part of this question, B2, said which aspects of the student's reasoning, if any, are incorrect? Explain how you arrived at your answer. And I think this was the tough part. It's important to realize here, they're saying the block is going to stop at position x equals 6d. And it is not obvious from the text of this you have to remember the original stopping position of the block was 3D. So the main thing that we really have to get at here is, well, what factor does that stopping distance change by? And that factor that the stopping distance changes by is a factor of 2. So now here's the deal. Essentially, what this kid is saying, and this was the critical thing to realize in terms of really being able to get the points for this part, essentially what this kid is saying is that the stopping distance will double because the spring compression distance doubled. And that ultimately is not correct. Because if you look at the equation for the elastic potential energy that we noted before, the elastic potential energy is directly proportional to x squared. And so the basic fact here that the spring compression distance doubled means the actual new potential energy is going to have increased by a factor of 4. And that's ultimately why this kid is wrong. The spring does store more energy, but it's not double, it's quadruple. And so what I wrote here is the student is wrong about the block sliding to 6D, which is twice as far as the original distance. The elastic potential energy is directly proportional to the square of the elongation distance. So if the spring is compressed twice as much, it'll actually store 4 times the amount of energy. This means that the distance traveled by the block won't be twice as far. Take a second to pause this video here, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, moving on here to the scoring guide. This was a 1-pointer, of course, for identifying the student is incorrect about the new final position of the block because the spring's energy does not scale linearly with its compression. Interesting. Now, that I think is a little bit of a weird way to write that the spring's energy does not scale linearly with its compression. I think the main point there is that you had to recognize that double the stopping distance implied that was because you had double the compression. But as we mentioned here, double the compression doesn't mean double the stopping distance because it has 4 times the energy. Take a second to pause this video here and write that down. When you hit play, we'll move on. All right, moving on to the nice part of this question here. It says, use quantitative reasoning, including equations as needed, to develop an expression for the new final position of the block. Express your answer in terms of D. Now, I want to be clear with everybody. When this test says use quantitative reasoning, what you should be reading is using the 1-1-1 rule, including equations as needed. No duh, the 1-1-1 rule always involves equations, to develop an expression. That's what they really want you to do here. Now, I'm going to be totally frank with you. The scoring guide doesn't really look like what we usually show for the 1-1-1 rule. But I think you will agree when I show you the scoring guide here in a minute, the way that we do it using the 1-1-1 rule is vastly superior to the way they showed it using whatever method they used. So let's go ahead and show that here now. The first thing you need to realize in order to be able to solve for the stopping distance is that the elastic potential energy stored in the spring is converted to the kinetic energy of the block once that spring is fully compressed. What we can also say here is that that kinetic energy, which for the purposes of the slowing down and stopping, is going to be initial kinetic energy. So we can say here the kinetic energy that the block eventually possesses is going to be equal to the amount of work that's done by friction. So the basic idea here is that putting those two equations together, we end up with an equation that says whatever amount of elastic potential energy this thing has in the beginning, well, that's equal to the work that's done by friction at the end. That's the basic idea. The work that's done by friction takes whatever amount of mechanical energy is present in the system and it converts it to heat. How can you tell that that's true? Because the block totally comes to a stop at the end. That's the idea. And so what we need to work with here now is this equation. The initial elastic potential energy is equal to the work that's done by friction. The first thing we're going to do is we're just going to expand this out as much as we can. We have 1/2 kx squared for the initial elastic potential energy, and we have the force of friction times delta x for the work that's done by friction. Now we have to go ahead and solve this for the delta x. So delta x here is going to be kx squared over 2 times the force of friction. And we might as well, and you should always get into the habit of this just in case there are cancellations. They're not here, but you should just get into the habit of this anyway, of expanding the force of friction equation to show 2 mu mg. The reason why you should do that is because Maybe the mass will cancel, or maybe something else will cancel, and then it'll be easy for you to deal with. Anyway, that's our equation for delta x. So now here we know that the only difference is that the new elastic potential energy is twice the old elastic potential, or excuse me, the new compression distance is twice the old compression distance. And we're looking for the new delta x. And so we have here delta x prime is equal to k times 2x squared over 2 times mu times m times g. And what that shows is we have 4kx squared over 2 mu m g. Now the question is, do you combine that with the 2 or not? You don't. That's in the original equation. So we have 4 times kx squared over 2 mu m g. And realize the 2 is in the original equation. So what this shows is delta x prime, the new stopping distance, is 4 times delta x. And what that shows, because the original delta x was 3D, is that the new stopping distance is 12d. The basic idea behind this calculation is this. The elastic potential energy is directly proportional to x squared. That means when they doubled the compression distance, the elastic potential energy quadrupled. Because the elastic potential energy is converted into kinetic energy, the kinetic energy of the block when the spring compression doubled was 4 times the kinetic energy as it was in the original trial. Because the block now has 4 times the amount of kinetic energy, and the kinetic energy is directly proportional to the stopping distance, the fact that it now had 4 times the kinetic energy means that it has 4 times the stopping distance. Take a second to pause this video here and write this down, adding any part of this that may be missing from your own work. And when you hit play, we'll take a look at the scoring guide. All right, moving on to the scoring guide here, it says you got 3 points for this part. 1 point for indicating that the final energy in the spring, which becomes the mechanical energy of the block as it reaches the rough track, is 4 times the original energy in the spring. Our work totally took care of that. We get 1 point for indicating the frictional force remains the same, basically just by not changing it. And then 1 point for equating the initial energy in the spring to an expression that shows the energy dissipated by friction is proportional to the distance that the block slides down the rough track. Now, it's not impossible to follow this, but I just don't think it is as clear as the 1-1-1 rule. They're basically saying U1 is 1/2 kd squared, so that means U2 is 1/2 k2d squared, so that means U2 is 4 U1. The elastic potential energy quadrupled. We get that. Then it's saying the work done by friction in the first case is the force of friction, mu mg, times the stopping distance, 3d. Then they're saying, well, the work done in the second instance is mu mg times this new stopping distance. Then they're saying, well, work 1 equals U1, and work 2 equals U2, and U2 is equal to 4 U1. So that means now the work is going to quadruple. And then basically they're just setting this equal to this to show that the friction force stays the same, so they all cancel, and that delta x2 is 4 times 3d, 4 times 3d is 12d. If you want to show it like that, go nuts. I think that that's insane. I think the 1-1-1 rule is much more elegant, much more clean, makes much more sense. There's a lot less hand waving, and it's like more obvious what we're doing. But either way, that choice is yours. Take a second to pause this video and take a look at the scoring guide. Make sure you understand all aspects of it. And when you hit play, we'll move on. Okay, moving on to part D. We see here now the question, and this question is annoying. They don't ask these so much anymore because I think a lot of kids had a tough time answering this the first year of the test, but it says, explain how any correct aspects of the student's reasoning identified in part B are expressed by your mathematical relationships in part C. Explain how your relationships in part C correct any incorrect aspects of the student's reasoning identified in part B. Refer to the relationships you wrote in part C, not just the final answer you obtained by manipulating those relationships. Okay, so there's a lot there. We need to explain how what the kid said is shown in our work. We need to explain how we corrected their wrongness. And we need to refer to the relationships we wrote, proportionality, really. So what I wrote here was the student was correct in indicating that the spring was going to store more energy when it was compressed farther, which means the block is going to slide farther. However, in our work, we showed that the spring potential energy increased by a factor of 4 when the spring was compressed twice as far because the elastic potential energy is directly proportional to the square of the elongation distance. Since the elastic potential energy is equal in magnitude to the work done by friction, since friction removes all the block's energy, the increased elastic potential energy results in increased work due to friction, which results in an increased stopping distance. The student was right about the increased stopping distance, but was wrong about the factor. The fact that the elastic potential energy is directly proportional to the square of the elongation distance means that when the elongation distance doubles, the stopping distance triples. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, moving on to the scoring guide here. Last part of this question, you got 1 point for indicating that the student's correct reasoning that the block had more energy in the second situation is expressed by the calculations comparing the initial energy of the spring. Talking about the proportionality is sufficient there. 1 point for indicating that the student's correct reasoning that the block will slide farther is expressed by an equation that indicates that the work that's done by friction is some factor greater than the work done in the first situation. And then 1 point for indicating that the student's incorrect reasoning that the energy scales linearly with the spring's compression is corrected by the expression for the initial energy in the spring. Take a second to pause this video here and write that down. When you hit play, we'll move on. All right, moving on here. Second question. I thought this one was much easier than the first one. Give you a little break after that toughie. This one says here, a toy consists of two identical solid spheres connected by a string with negligible mass. The toy is thrown at an angle above the horizontal, not straight up, such that the string remains taut and both spheres are revolving counterclockwise in a vertical plane around the center of the string, as shown above. The first part of this question here says sketch graphs of the horizontal and vertical components of the velocity of the center of the string as a function of time, from the instant the spheres are released at time t equals 0 until the instant the system returns to its initial height at a time t final. Take the positive direction to be toward the right for the horizontal component, and take the positive direction to be upward for the vertical component. There's a lot of important information here. Notice they're telling us about the velocity of the center of string. That's where the center of mass of the string is. And it's really important for everybody to remember when we are dealing with extended objects like this, we have to remember that the motion of the center of mass is the same as the motion of like any other particle. That's an important thing to understand. That in this particular situation, the velocity of the center of the string is going to look like the velocity of literally any other projectile. So basically, they're just asking us, draw the horizontal and vertical projectile graphs for an object thrown at an angle. When an object is thrown at an angle, its horizontal velocity is constant. The horizontal acceleration is 0 meters per second squared. And so that means on this graph here, we should show a line with no slope, basically. And that's that. AX equals 0 meters per second squared. That's it. Take a second to pause this video here and write down that graph. When you hit play, we'll move on to the vertical. All right, moving on to the vertical graph. Now we have to sketch the vertical component. It's very important to remember we've got to show a couple things on this graph. The first thing is that the velocity in the vertical direction for a projectile that's fired at an angle, remember the trajectory looks like this, the vertical velocity starts positive. In the middle, it goes to 0. And then at the end, it goes negative. And of course, this graph has got to be a straight line because the slope of this graph is going to be the acceleration due to gravity. And so this graph has to have a constant negative slope of negative 9.81 meters per second squared. And so the graph is going to look a little something like this. Of course, it's not going to be drawn so terribly, but of course, you're going to have a straight edge for the AP test. So you're just going to use a ruler, draw a nice straight line, and that's that. Now I'm just going to turn off this slide because both of these are shown on the scoring guide. And I wanted to make sure I didn't forget to say this. And so here it is. Notice here, they give you 1 point for the horizontal component graph by just showing a non-zero horizontal line. It could have been anywhere. I drew it at the top, so did they. And you got 1 point for a non-vertical line with a negative slope that crosses the horizontal axis near the halfway point and then reaches T final. Notice this graph also honors the concept V launch equals the negative of V land. When this thing at time T final reaches the time that it reaches its initial height, by that time T final, it's showing that the landing velocity is the negative of the launching velocity. That's because if this object is accelerating over the same distance with the same magnitude of the acceleration, then it's going to experience the same speed change. That's an important thing to realize. Take a second to pause this video here and write that down. When you hit play, we'll move on. All right, and just to finish this thing up, let's move on to the last part, part B. This one has 3 subparts, but they're all pretty quick. It says here, the figure above shows the toy at the instant the center of the string reaches the top of its trajectory. This is a side view. The sphere on the left is higher than the sphere on the right. It says on the dot below, which represents the left sphere only, draw and label the forces, not components, exerted on the sphere, on the left sphere at this instant. Represent each force by a distinct arrow starting on and pointing away from the dot. The dashed line is drawn at the same angle as the string. Now, it should be obvious to everybody, at least I hope it was, that this left sphere very obviously has a force of gravity acting on it. But because we are talking about the left sphere here, we also have to account for the force exerted on it by the string. Now, as the problem said, this thing is rotating counterclockwise. It's rotating. That means there must be a centripetal force acting on it as well in order to make it rotate. And that force is the tension. It should be clear also that this thing is going to want to fly off in the direction tangent to the circle because of its own inertia. And so the string has to pull on it inward, like this really, in order for it to continue moving with the other sphere. So this object, this left sphere, has 2 forces acting on it: the weight and the tension from the string. The key idea here is that they're asking you about an individual sphere, and the individual sphere has the force of gravity and the force of tension acting on it. In this scoring guide part here, they give you 2 points for this. You got 1 point for gravitational force with the correct direction and label, and you got 1 point for the tension with the correct direction and label. If you drew any extra forces, you only could get 1 point. Take a second to pause this video here, write that down, making sure you understand all aspects of the scoring guide. When you hit play, we'll move on. All right, moving on to the next little subpart here. Subpart 2 said, now you're drawing this same diagram for the last one, but except it's for the whole toy, the sphere's string system. Remember, these free body diagrams are always diagrams of the forces acting on a particular object or a particular system. And while it is true that the force of gravity definitely acts on the whole system, the force of tension does not. The force of tension is a force that is internal to the system. And so the only force that is acting on the whole toy is the force of gravity. That's a really important thing to understand. Gravity is the only net force. The tension is an internal force. It should also be noted, although this might not be totally obvious, since the tension on that sphere, the left sphere, goes this way, and the tension on the right sphere goes this way, there's no net force associated with the tension on the whole system. That's why the free body diagram in the scoring guide looks like this. You got 1 point for the gravitational force with no extra forces. Now, the scoring guide does say a label is not required since the use of labels is assessed in part B1, but follow the directions. If it tells you to draw and label the forces, draw and label the forces. Don't lose a point for something as silly as that. The only other thing to say here about this scoring guide is if you drew anything extra, you got nothing for this. Take a second to pause this video here, making sure you understand all aspects of the scoring guide. When you hit play, we'll move on to the last part. All right, moving on to the last part here. I like this question. It says, when the toy was released, the center of the string was moving with an initial speed of 15 meters per second at an angle of 60 degrees above the horizontal. So we had a 15 meter per second velocity at an angle of 60 degrees. It says, calculate the speed of the center of the string at the instant shown above when the center of the string reaches the top of its trajectory, or in other words, the maximum height. Now, I do believe I asked you a question like this on the projectile motion test. A lot of people get fooled into thinking that at the maximum height, the velocity is 0. That's not true. Only the vertical velocity is 0. The horizontal velocity is going to be equal to the initial horizontal velocity because for a projectile, there's no acceleration in the horizontal direction. That's a super crucial, important thing to understand. So it's really important to realize for this question here, basically by asking you for the speed at the max height, they're just asking you for V naught x. That's it. And V naught is 15 meters per second, and the angle is 60 degrees. And so finding V naught x is super easy. V naught x here is equal to V naught cosine theta. And that means this is going to be equal to 15 meters per second times the cosine of 60 degrees. And so that means V naught x is going to be just half of 15 because the cosine of 60 is a half. And so this is going to be 7.5 meters per second. That's it. Now I'm just going to skip directly to the next slide here because the scoring guide shows this. They give you 1 point for attempting to find the horizontal component of the velocity. This is crazy that they even give a point for this. The point is earned for the wrong use of trig functions if it is being clear that it is being used to find the horizontal component. That's insanity to me. If you write V sine theta here, that's wrong because the horizontal component is based on the cosine. If then you write Vx, which is doubly wrong because the sine goes for the vertical component, that gets you a point. So this, singularly wrong, no points. This, doubly wrong, points. Okay. And then it says 1 point for a correct numerical answer with correct units. So notice, if you wrote V sine theta equals 13 meters per second, you got no Vx, you got nothing. Here, you wrote Vx, still dead wrong, but you got 1. Congratulations to you. You got 1 point if you just wrote V cosine theta because you got no answer. And then, of course, the 2 point responses here are shown here. They gave you 15 cosine 60, no units anywhere except at the end. I wouldn't give that, as you know. That's why you guys are going to destroy this test because you are better prepared than most. And then 2 points for 15 cosine 60, no units, and then just meters per second at the end. Okay. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll wrap it up. All right, everybody, that is it for today. Now, that last question I hope wasn't too terrible. That first question I thought was pretty tough. Again, that came from the AP Physics 1 exam, the first year the exam ever existed. It is kind of difficult. They don't really write questions exactly like that so much anymore, but I think there are a lot of really super important concepts and skills in that question. And so I hope you really paid attention to this video and picked up some of those little tips and tricks along the way. Obviously, as is always the case, if you have any questions, let me know. But with that, that's it for today. Have a good one, everybody.